In this video, I will explain a complete AI-powered smart energy management system developed in MATLAB. This project combines deep learning, load forecasting, renewable energy integration, battery energy system storage, time of use electricity pricing, and state space model predictive controls to create an intelligent microgrid energy management system. So the objective of this system is very simple. The modern power systems face three major challenges. So the first challenge is electricity demand, and the second challenge is renewable energy sources such as solar power, and third challenge is increasing electricity cost and carbon emissions. This system combines deep learning using a three-layer LSTM network and real-world PJM electricity data, model predictive control, battery energy storage system, time of use of electricity pricing, and smart grid optimization. We will talk through the complete architecture, forecasting model, and optimize framework, benchmarking results, and final dashboard. So first of all, we discuss about our project overview. So I'll show you our project, our system architecture. So we move here. Here is our architecture diagram. So first of all, you can see PJM load data. PJM, basically this is a data set for electricity demands and loads. So first of all, we load our data set, then we move to the data processing here, data processing, then we move to our feature engineering, then we have a LSTM model, three-layer LSTM model network. Then we have 24 hours load forecast, then State-Space MPC. Then we move to our battery, solar, and grid. Then we have cost and carbon, CO2 optimization. Then we last have a dashboard. So this is basically our architecture, working architecture. So now we move to the next. The objective of this project is build a research-grade microgrid energy management platform. So this system first collects historical electricity demand data, and advanced feature engineering is then perform a create meaningful platform patterns for machine learning. Then a deep learning LSTM model forecasts the next 24 hours of energy demand. These forecasts are sent to a model predictive. Model predictive. So, and the controller of our system demonstrate how much energy should come from solar PV, battery storage, and from grid, while minimizing energy cost, grid dependency, and the carbon emissions and battery wear. Now the question is why we need smart energy management. So the simple answer is load energy cost and reduce peak demand of energy, and better battery utilization, a high renewable penetration, and lower carbon emissions. Now the traditional power systems operate electrically, and energy is generated after demand occurs. Modern smart grids operate pre-activity. Using artificial intelligence and predictive control techniques, future demand can be estimated before it happens. This enables better battery utilization, reduce peak demand, lower electricity bills, increase renewable penetration, reduce carbon footprint. These technologies are currently used in smart grid microgrids, and commercial buildings, data centers, and renewable energy plants. Now we discuss about our data set. Now we our discuss about our data set. Now we have our data set code here. So we have a live API integration here. You can see first we download our dataset from PJM Dataset. Now download from here and save our dataset. Now you can see here our datasets are available. Now we discuss about our dataset. So first, for this project we used the PJM interconnection electricity dataset. So the PJM is one of the largest electricity market in North America. Historical Harsley load data was extracted. Here we can see Harsley dataset. Here we can see our Harsley dataset. So our final operating conditions: average load 61 kilowatt, peak load 94 kilowatt, solar capacity 60 kilowatt, and battery capacity 300 kilowatt per hours. Battery power rating is 50 kilowatt. This configuration closely resembles a commercial building or small company's microgrid. So now we discuss our feature engineerings. Now we move to our feature engineering codes. Here. So now we can see here our raw PJM data load. Now we can see here our raw data load. Now we can see here raw PJM data load. Then we move to our feature engineering. Here we extract load, temperature, solar, hours of the day, days of the week, and a rolling mean, a rolling stand, each and everything. So 11, we use here 11 features. And then we move to our last into our LSTM model forecasting. Raw data alone is not significant for accurate forecasting, so therefore we use 11 engineering features were created. These include load features like historical load, 24 hours load, 168 hours lag, and rolling mean, rolling stand divisions. Now the time features, we use hours. Here we use time features. Yes, here our sign, our cosine, day of week sign, day of week consign. Here we use in our code. Experimental features, we use temperature and solar. These features help the neural network learn daily and weekly consumption patterns. So now we move to our LSTM model. Move to our here LSTM model. Now first of all, you can see here layers of our model. So first we have layers of our model. I can see here, you can see here LSTM model layers. First of all, we have input layer, then we have LSTM 128, then LSTM 64, LSTM third layer, fourth layer 32, then fully connected. Then we have 24-hour forecasting. So this is our LSTM architecture. The forecast, yeah, now we move to back here. Here our layer system. Now we have our training options. The forecast future demand, a deep learning architecture based on long-term short LSTM, long-term short-term memory network was developed. LSTM network are specifically designed for time series forecasting problems. So unlike the traditional neural networks, LSTM can remember long-term temper dependencies. Our architecture consists of first LSTM layer 28, and I already explained. The model receives 24 hours. So the next thing is during training, we have 21,006 training sequence. Now we have explaining our training options. So 280 validation sequence, 3 4 to 3 4 to 3 training testing sequences. So we have during training we have 21,006 training sequences, 280 validation sequences, 423 testing sequences were used. So now we move to our forecasting result. Now we run our system and look for the results. Now our system is running successfully, and you can see here the feature load, temperature, each and everything from the. Now you can see here requesting HTTP. We are requesting to the API. Now our LSTM training started. Now we need to wait to complete the training. Our training is almost complete. Just wait for output. Our dashboard will now open. Generating dashboard. So then we will discuss our result. Now this dashboard is open, and now we see here our dashboard. Now first of all, we can see our load forecast versus actual. So there is after running the forecasting model, we achieve RMSD 8.05 kilowatts. You can see here 8.05 kilowatt, and ME is 6 point. Here you can see ME 6.05 kilowatt, and MAPE is 8.7%. So the mean absolute percentage error below is 10%. So here you can see our mean is below the 10%. Demonstrate a strong forecasting and capability for a 24 horizon. The forecasting output is then used by the optimization engine to make intelligent energy scheduling directions. So now the second plot, our second plot is grid power. The grid is used whenever solar and battery power cannot fully meet the demand. Means we need our grid power when then battery and solar are not capable to produce the maximum load. During the simulation, grid impact is 467,469,180 kilowatt per hours, and grid export is 0 kilowatt hours. Grid share is 706%, means 70.6%. This means almost 30% of energy demand was supplied locally by solar and battery resources. Now we last is our battery storage SOC trend. A battery storage system or BSSC is integrated microgrid specifications. Our battery capacity is 300 kilowatt per hours. Maximum charge power is 50 kilowatt. Maximum discharge power is 50 kilowatt. The battery sources, battery stores excess solar energy during low demand periods and supplies energy during expense peak periods. Energy source mix. So now we move to our dashboard second page. Here in the second tab, there is a energy source mix over time. So there is the total energy consumed was uh, here. If we total all of this solar, battery and grid, the total energy was 66488 kilowatt per hours. And energy contributions for grid, solar and battery. The solar producing 150 comma 474 kilowatt hours. Battery is producing 65 comma 920 kilowatt per hours, and grid is producing 469,180 kilowatts. So renewable energy provided 22%, almost 23% of the model of the total demand. So total demand. So the second here is battery performance. Average SOC is 42.6, peak SOC is 89.3, min SOC is 20%, and battery total capacity contribution is 6592 kilowatt hours. And here is sustainability impact. So results show CO2 avoided double eight 0 to 4 kilogram, and renewable energy 22.6%, and cost saving is 29.4%. This shows the system is both commercial and environmentally friendly. The next is cost saving. So there is a total cost saving. Here is our table: RMSE, total energy, then MAE kilowatt, MAE battery energy, R2 score, and forecast accuracy, 91% grid dependency, and this total cost saving is 29.42. And by combining load forecasting, solar generation, battery scheduling, and MPC optimization, the system achieved cost saving of 29%, almost 30%. This means the microgrid used energy more efficiently and reduced expensive grid power. Now we move to our model predictive control. So model predictive control, here is our model predictive control visuals. Forecast demand, then we use our MPC optimizer, and then we have a solar, battery and grid. The heart of this project is state-space model predictive control. And here is our comparison. So MPC use future forecast to make present decisions. At every hour, the controller predicts future system behavior over a 12 hours prediction horizon. Any optimization problem is solved using MATLAB, and the controller maximize energy cost, grid impact, battery wear, carbon emissions, while satisfying power balance constraints, battery limits, and grid constraints. This allows the controller to intelligently determine the best charging and discharging strategy. So now we discuss our benchmark comparison. Benchmarking study so to evaluate performance for four different energy management strategies were compared. Here, the first strategy one is not no battery storage. No battery storage. We can see here our first no battery storage. Then role-based energy management system. Second, role-based energy management system, and the third is time use of aware energy management system. TOU aware. Here is TOU system. And here we are comparison of both economic performance comparison and grid dependency comparison. So there is strategy 4 State-Space MPC. Here true MPC, and result show MPC grid dependency 70.6. Grid dependency 7.6. Carbon emissions from reduced from 230,172 kilogram to 211,131 kilogram, and nearly 30% operational saving compared with conventional operation. The result explain the effectiveness of predictive optimization in smart system. So our basically our dashboard, professional dashboard is developed in MATLAB to visualize the system performance, and the dashboard result includes forecast versus actual demand, error distribution, energy state of charge, grid impact analysis, renewable energy contribution, cost savings, carbon reduction metrics. This transforms raw simulation result into actionable operational insights. If we tell about real-world applications, this framework can be extended to smart buildings, university campus, industrial facilities, EV charging stations, renewable energy plants, and community microgrids. The same architecture can also be integrated with real weather APIs, real-time electricity markets, IoT sensors, and SCAD systems. So our conclusion is, in this project we developed a complete AI-powered smart energy management system using MATLAB, and this system integrates deep learning forecasting, LSTM network, energy storage, solar energy, model predictive control, time of use of pricing, smart grid optimization. This project explains how artificial intelligence and advanced control work together to create efficient, sustainable, and intelligent energy systems. If you enjoyed this project, please like video, subscribe to the channel, and let me know what MATLAB or AI project you would like to see next. Thank you so much for watching.